Hello, this is the presentation for Assignment 5, which is going to cover the topics of data mining, optimization, and networks. Specifically, we're going to discuss airborne weather radar and a study of repair data to optimize reliability of weather radar units. What is the function of weather radar? Well, it's to provide the flight crew with real-time awareness of weather conditions in the flight path. Specifically, this improves safety through the detection of wind shear on takeoff and landing. It improves passenger comfort and it permits continued operations in bad weather. This is where the weather radar module is installed on an aircraft attached to the firewall. It transmits high-frequency radio signals, which are then reflected from precipitation. The receiver processes it, and it is then converted by a processing assembly into an image which is displayed in the cockpit. This is what it looks like in the cockpit. We're going to focus specifically on the weather radar module, and these are each of the assemblies that make up the weather radar module. The RF assembly contains the receiver and the transmitter, which interface with the antenna. The digital processing module performs all processing to generate the image. The pedestal contains the motors and the gears, which move the antenna from side to side and up and down. This is what it looks like. We are going to mine repair data to identify areas for product improvement. We have 230 records from 1 year of removals, and this is what a repair record looks like in terms of the attributes. We are going to focus on the class attribute, which classifies failures according to a root cause, either process, random, wear out, design, or other. The class attribute is determined by engineering analysis. It can be a time-consuming process. Specifically, our objective is to identify trends within the process, wear out, and design categories, because those are the best opportunities for implementing a corrective action on the fleet. Random failures are much more difficult to address. This is a snapshot of a sample of the records just to show how they're populated. And this is an analysis of the class attribute, and it shows, as would be expected, of a lot of random failures, but also a lot of design failures and wear out failures, and these are the areas for opportunity. So when we develop a decision tree in Weka for this data, we immediately see that at the top of the decision tree we have these fields: SB1 Service Bulletin 1 and SB2 Service Bulletin 2. If we follow these branches for SB1, so what this means is if Service Bulletin 1 is not installed, then we have a very likely outcome is a design failure on the A3 card. It just so happens that Service Bulletin 1 implements a design fix on the A3 card, optimizing the tuning of the power amplifier on that assembly. Similarly, SB2, which improves the sealing of the motors to prevent water intrusion and premature wear out, if Service Bulletin 2 was not installed, there was a high likelihood of premature wear out failures due to that reason. So the conclusion from this data mining exercise is we actually have two very good fixes already available, Service Bulletin 1 and Service Bulletin 2. We should work on getting them implemented throughout the fleet. Further analysis through data mining and looking at the time to failure attribute further confirmed that the classifier was correctly identifying wear out failures. So we need to implement Service Bulletin 1 and Service Bulletin 2. Looking at this becomes a optimization problem. We want to implement these service bulletins, but there's some constraints. There's the cost, there's the availability of motors for Service Bulletin 2, and there's also a limited number of units that actually need Service Bulletin 1 and Service Bulletin 2. So we can generate an optimization problem. From a side calculation, we determine the reliability improvements due to SB1 and SB2 independently, and then we can generate this maximization equation here for maximizing the reliability improvement, subject to these cost constraints where our total cost and the cost of implementing service bulletins, either SB1 and SB2 or SB1 and SB2 individually. This completes our linear programming model here. C3 through C5 are constraining the maximum number that we can implement for these service bulletin combinations, depending on how many are actually out in the field. Obviously, we can't implement SB1 and SB2 on more units than actually need them. Running this through the Excel solver, we develop our solution here, which is that both service bulletins should be implemented on 237 units and only SB2 on 88 units. That meets all the constraints of our analysis. This is an interesting solution because it implements the more expensive service bulletin 2 rather than SB1, which was a lot cheaper, which is the opposite of what would happen in reality. Usually managers tend to implement the cheaper solution first. So this is an interesting solution. Finally, we look at the repair center network, and this diagram is based upon the repair data that we used for data mining. And there's some interesting properties from this network. First of all, we can easily see the prominent vertices. These are Hamburg and Dallas with in-degree centrality metrics of 13 and 7 respectively. Another interesting property is the minimum vertex cover. As would be expected, the 5 locations with repair capability are incident with all edges in the network. However, if we removed repair capability from Hong Kong, we could accommodate all Hong Kong's repairs using edges that already exist in the network. That concludes the presentation. Thank you.